First talk will be given by Shira Chapman. So welcome Shira to this workshop. And she is from University of Amsterdam, and she will talk on complexity and black hole. So I will now hand it over to Shira to start.
Thanks a lot. Can you hear me? Just nod if it's
yes.
All right. Awesome. Okay, so hi everyone. I'm very glad to be here. Today I'm going to talk about some very interesting set of ideas that came up in the context of the ADS-CFT correspondence, which relate gravitational problems to measures from quantum information. And in particular, I'm going to focus on the idea that the geometry behind the horizon of a black hole is encoded in a quantity that is known as a quantum computational complexity. And I'd like to encourage you to ask as many questions as you want. Either unmute yourself or you can put it in the chat and the moderator will read it to me. So you should feel really free to ask. All right, so just some introduction to get us all on the same page. The idea that black holes are related to quantum information dates back to the Bekenstein-Hawking formula, which gives us a very simple formula relating the entropy of a black hole to the area to the area of its horizon. And more recently, Ryo and Takayanagi have proposed a formula relating the entanglement entropy to the minimal area of a surface that goes through the bulk and ends on the region where the entanglement entropy of we are interested to measure. I think we have a Ida, could you perhaps mute yourself? Sorry. Thanks. All right, so these ideas have led to very interesting developments, including ANC theorem, studies of thermalization, chaos, scrambling, etc. And it also provided a very useful tool for understanding which parts of the bulk are encoded where in the boundary. Now, the next station in the story is a puzzle about black holes. The point is that even though from the outside black holes appear to stay constant in size, the interior volume keeps growing bigger and bigger for a very long time as space stretches towards the center point. And so this leads us to a puzzle, since we know that the holographic correspondence is supposed to encode every property of the bulk in the boundary. This leads to a question of how this growth is encoded in the boundary. And since we don't know many quantities that grow for a long time, that's kind of a puzzling aspect. And that led Saskin to make a proposal in 2014 that the interior volume, or the volume inside the bulk, is actually related to a quantity that is known as quantum computational complexity. That's what led our community, the holographic community, to start studying complexity. So before I proceed to the core of the talk, I just want to say that I was very lucky to work on this with many talented people from all around the globe. And who knows, maybe after this conference, I will be able to add collaborators in India too, hopefully. All right, so that's an overview of how my talk is going to look like. It will have three parts. The first part, I'm going to give an overview of complexity, just explaining what's the definition of complexity and what properties we expect from it. The second part is going to be about defining complexity in quantum field theory. And I will tell you about very simple models in which complexity is well understood in field theory, both for pure states and mixed states. I will also highlight what are the current open problems. And the third part is going to be going back to the black holes, about holography, telling you a bit about the time dependence and how complexity reacts to perturbations. So first things first, I start with a definition. So what is quantum computational complexity? Complexity is a property of a quantum state, which is defined as the minimal number of simple unitary operations that one has to put together, starting from a simple reference state in order to get to a target state of interest. So in simple words, it's just how hard it is to build a given state, starting with a very simple state. I like to break this definition down on chains of spins or qubits, where the definition is very well defined, although of course not that easy to calculate. And the idea here is to start with a simple unentangled reference state, for example, a state where all the spins are pointing up in a chain of m spins, and start applying simple universal gates to construct a quantum circuit. So simple means gates that act on a small number of qubits, 1 or 2, but in any event, a number smaller than the size of the chain. And when I say universal gate, I mean gates that approximate to arbitrary accuracy any state. And you can see here in the box, that's an example of a set of simple universal gates, gates that act on 1 spin and gates that act on 2 spins. And with these gates, it turns out that you can get as close as you want to any state of interest. Now, the idea is simply that I start with the reference state and I multiply the gates one by the other in a series of unitaries, such that I build a unitary that leads me from the reference state to the target state. But since the gates are discrete, for example, in particular in this example, not always, but in these examples, the gates are just like 3 of them, I cannot really get to the whole continuum of states on the spin chain, but I can get as close as I want. So I also need, inside the definition of complexity, to talk about a tolerance, meaning that I am going to get to a state that is not quite my target state, but close to or to a level epsilon from the state I'm interested in. And that's it, basically. Then the complexity is the minimal number of gates that are needed to get from the state I start with to the state I'm interested in. Now, 2 comments. One is that you see that the definition of complexity depended on many choices. It depended on the choice of gates and on the choice of the reference state and the tolerance. But so I should actually think about complexity as some family of measures, like the Renyi entropies have indices m. The complexity has 3 indices: the gates, the reference state, and the tolerance. But some properties are going to be universal, and that's what I'm going to talk about in the rest of my talk. And of course, to put things in context, I should say that we were not the first one to invent quantum computational complexity. It's a very common field of study in quantum information, especially for the purpose of performing quantum computations, where you have a quantum computer that uses superposition to perform a computation in parallel on many inputs, and the bottleneck in the quantum computation is to prepare the input state for the computer. So from this point of view, it's also, of course, very important to estimate what's the complexity of a given state. Okay, so all this has been about the complexity of states. I can also define the complexity of unitary transformations between n qubits by a very similar definition. So basically, if I'm interested in a given target unitary, I'm going to ask the question, what is the minimal number of gates that I have to multiply by each other to get close as I want to the target unitary, closed to a distance epsilon. Now, a few facts that will play a role much later when I talk about the time dependence of complexity about the group SU2 to the m is that the furthest unitary from the identity in this group lies at a distance which is exponential in the number of spins from the identity, and the volume of this SU2 to the n is doubly exponential. So if I basically chop it to boxes of size epsilon, I will find doubly exponential number of such boxes inside SU2 to the n. Okay, so both the states and the unitaries complexity that I was talking about are based on the discrete gate counting. So you saw we basically multiplied gates in a discrete way, one after the other, and this has some drawbacks. First, it's sensitive to the arbitrary tolerance, which is not that great. And second, it's discontinuous, which means that I can have an overshooting problem. I could have I could be quite close to my unitary, to my end unitary, and just overshoot and overshoot and overshoot, and it would take a long time to approach it in, say, kind of a spiralic way. But that would be a funny definition. It wouldn't really represent the intuitive notion of distance. So that makes it desirable to look for a continuous definition. And in addition, a continuous definition is, of course, also desirable when we are interested in QFT and in gravity, where we are used to work in the continuum. So that's what Nielsen did for us. Nielsen proposed, still in the context of spin chains, a continuous definition of complexity, where he was translating the problem of finding optimal circuits to a geometric problem of studying geodesics on the manifold SU2 to the n. And here, the basic idea is that the elementary generators of SU2 to the n, that we often call TA, induce motion in the group manifold. So we can move in a continuous way by turning on prefactors to these generators. And then there is a very natural metric on the associated Lie manifold, which we can choose to prioritize simple gates, so gates that have a small number of spins. And this results in the fact that we just study continuous trajectories rather than discrete ones. A small historical footnote is that Nielsen originally used this to provide a bound on the discrete gate complexity, rather than being exactly interested in what is the length of the geodesics. But of course, when we will go to QFT, we are going to use his ideas and similar ideas of continuous complexity as a definition, precise definition of complexity in field theory. All right, so that was an introduction, and maybe I should pause for questions if anyone has questions, and then I will move on to tell you about complexity in QFT.
So I think there is one in the chat actually. One question in the chat I can see.
Can you read it for me?
Yeah. He said that its complexity is unique.
Right. So that's the answer is no. Complexity is not a unique measure. It has many sub-indices. Like, you should again think about it like the Renyi entropy sub-index n. So you should think complexity with a lot of sub-indices telling you what are the gates and what is the reference state that I start with and what is the tolerance, etc. But with, say, reasonable definitions, so if the reference state is simple, meaning unentangled, and if the gates are simple, meaning that they act on a small number of qubits compared to the size of the chain, you will see that certain properties, for example, how the complexity diverges and depends on the central charges, etc., is going to be universal. So I will be able to make statements that are independent of these choices, but the complexity is not one measure, it's a full family.
Another question is, somebody is asking is that, what is tolerance?
Oh, yeah. So tolerance is a way to define how close I want to get to my target state. So if you think about the spin chain and you think what is the most general state that I can build on the spin chain, actually I'm going to use the annotation. Then the most general state that I can build on a spin chain, you can see what I'm writing, right?
Yes.
Is going to be, you know, a complex phase times up, and another complex phase times up, down, etc., plus, and so on. So 2 to the n combinations of the spin orientations, and 2 to the n maybe up to an overall normalization, generic prefactor, complex prefactor. Now, the point is that these numbers are continuous, and I'm trying to get to all this continuum with 3 gates. So I can't actually do that since the gates are discrete. There are just 3 of them. But by applying them in all the different orientations, I can get as close as I want, meaning that I will get to a state psi epsilon that is not quite the state I wanted, but it will be close to the state I want to order epsilon. Or for the unitary, there was a similar definition that used trace. So I won't actually get to the target unitary I wanted, but I will get to something that is very close to the target unitary that I wanted.
Perhaps one last question is that again, so question is that why is it not possible to make the epsilon to 0?
Well, I think this is like you know, saying that I can get to as close to pi as I want by taking a series of integer over integer, but I cannot write pi as integer over integer. I think that's the point, that this is a continuous variable, and the gates are discrete, so it's like trying to approximate pi as integer over integer. It's kind of the same task. I can build a series that goes as close as I want, but I can't actually write it as integer over integer. It's not
Shira,
the same cardinality. Yes.
Shira, are you assuming that you have ideal gates? I mean, even experimentally, when you try to make gates, there must be some errors in the gates themselves.
Yes, you're definitely right. I mean, at the moment, I'm simplifying a lot. I think when you go to experiments, indeed, you would have gates that are imperfect, and you would have to take into account this imperfectness and also in how close you get to your end state. But we haven't studied that. But I think that's a very important point. Okay, so let's move on. Okay, so let me tell you a little bit. So I told you that my original motivation is to study the interior of black holes, because it turns out that there is some geometric properties inside black holes that behaves morally similar to the way complexity behaves. But of course, the original arguments were based on morally similar, meaning that complexity behaves in this way in spin chains that we know, but there was not really a well-defined definition of complexity in quantum field theory. And at this point in time, there has been a number of developments, starting with defining complexity for free field theories, and then there are additional developments about interacting field theories, a little bit about weakly interacting field theories by, I think, some people in the audience. And a little bit of progress in CFT, but we are still far from really having a very good definition. But let me present to you the first steps. So,
Shira, I had just a small question. You said complexity, the way you defined it was through gates, that how many gates you require or something. But can I not ask the question totally theoretical in the sense, suppose I want to go from state 1 to state 2, and I have a Hamiltonian given. And I know I can evolve with the Hamiltonian, and I know after how much time I will be able to reach there. And depending on the states, it might take more time or less time. So is there a way to give a theoretical measure rather than this way of thinking in terms of gates?
Yeah, so you would like to, I mean, I'm not sure if I'm reading correctly your question, but I mean, are you interested in asking how complex is the time evolution of a given system?
Yeah, what I was asking is that, how complex, that's one question, but I would rather like, is there a theoretical definition other than defining in terms of gates, that how many gates do I require to go from one state to other? I would like to have a more dynamical question that, if I want to reach from one state to the other, and given how much time it requires, so there is a dynamical parameter that if it is larger, I'll say complexity is larger. Is it possible to define that way?
I mean, I think that maybe the name gates is a bit misleading in the sense that, of course, you can think about two Hamiltonian evolutions, and you could iterate Hamiltonian evolutions for different amount of times, which would be quite similar to what I call gates. I mean, I know that, so I don't know if you know, but there are these people trying to build the thermophile double state in the lab. And these people, they started like some kind of series of Bell pairs, and they have two Hamiltonians, and they apply one for a certain amount of time, then another for a certain amount of time, then again one, and etc. And I think eventually these Hamiltonians are what you would call gates in this construction. So they are, I don't know, combos of generators of SU2 to the n. So in the continuous definition, it's very, very similar to applying, or practically the same as applying Hamiltonians, different Hamiltonians for a certain amount of time. The problem with applying a single Hamiltonian is that you're really not capturing the complexity of the state in just asking how long the Hamiltonian has acted, because if you think about a very, very simple free field theory, for example, the state is oscillating, or even think about a single harmonic oscillator. And so just asking how long the Hamiltonian has acted is not the simplest way to build the state. You have shortcuts. Since the state is oscillating, you could apply the Hamiltonian for much shorter time than the whole evolution time and still get to the same state.
Okay, okay, thank you.
All right, so okay, so I'm going to tell you a bit first, a very simplistic model for how we define complexity in QFT. So in order to define complexity in QFT, we have to choose a number of different things that we talked about. So we need to choose a state where we start. What is a simple state? What does it mean to be a simple state in QFT? We need to choose a target state where we want to get. We need to select allowed gates or maybe Hamiltonians. We need to define a way to measure the length of a given circuit. So to associate a distance function that tells me which gates cost more than other gates. And then technical points that we need to know how to find the minimal circuit with all these definitions. And one point that is special to QFT and did not exist in spin chain is that in QFT complexity is divergent. And this is from a very similar reason to the one for which entanglement entropy is divergent. This is because we need to build the entanglement up to arbitrarily short length scale to construct the state. And since 2-point functions, for example, diverge at zero distances, we have to regulate this somehow. So we have to either put the theory on a lattice or use a UV cutoff. And so what we will see is that we need to find a way to do that. So we will, in our case, we will use a UV cutoff, but there are other ways, of course. So what we did in the paper with Michal Heller, Hugo Marocchio, and Fernando Pastavsky was to look at a free scalar QFT, which is the simplest model we could come up with the following Hamiltonians. So with the momentum and the field operators turned in this way. And we focused on Gaussian states, which are much easier to handle than other states, since you have a closed set of gates that guides you between them, which are the quadratic operators. And what we wanted to build, so our target state, we chose to be the vacuum state. That's a very natural state that one would want to build in a free QFT. This vacuum state is Gaussian in this case and has a 2-point function which depends on the frequency, the characteristic frequency, square root k squared plus m squared. Now, in what I'm going to tell you is going to be convenient to keep track of the coefficients of the 2-point function as a function of momentum. So that's a characteristic plot for the ground state in momentum space. This is for the massive case. This is for the massless case. In position space, it basically means that the correlations are decaying, but are blowing up when the 2 points are the same. These are the UV divergences. For the reference state, I told you that I was looking for a simple unentangled product state. Now, the reason that the vacuum is very entangled, that if I cut a region out of it, I get some entanglement entropy, is this derivative term that couples sites to the sites next to them. If I turn it off, and okay, I don't necessarily have to consider the same mass. I could have a certain choice of the mass of the reference state. Then I will get a state which is unentangled, whose coefficients in the 2-point function are simply constant. And this, if I transform it back to position space, I'm simply going to get a delta function, which means that the different sites don't know about each other. Again, the unentangled property. So when I try to study the complexity of the ground state, what I want to do is I want to go from the green reference state to the vacuum state. And of course, I have to do this for an infinite number of different momenta. And that's the reason why I have UV divergences. And one way to regulate it is just put a cutoff. So put the cutoff, well, not necessarily exactly at the intersection of the curves, but put a cutoff and only transform the reference state to the target state up to a certain cutoff. All right, so now we have a lot of components, so we know that we are starting with the reference state, going to the vacuum along series of state psi of sigma. Sigma is a path parameter running from 0 to 1. And now I need to tell you what's the distance function that we chose and what are the gates, etc., etc. So for the distance function, there are a number of different options. One that is very symmetric is the Fubini's 2D metric. That's the one we studied in our paper. That has basically the advantage that it mods out the overall phase from the state. So if I'm just adding to the state and overall phase, this is going to cancel between these two components of the Fubini's 2D metric. And so I will be left with something that doesn't depend on overall phases, which is kind of nice. Complexity, oh, and of course, there are similar results that basically give this exactly the same by Roe Jefferson and Rob Myers using a Nielsen distance that does give some effect to the phases. But for generic properties like the UV divergences, etc., they behave in a very, very similar way. Now, the complexity, as we said before, is the minimal circuit length using the distance function. And for the gates, since we are moving between Gaussian states, we are going to use quadratic gates. This is, for example, a subset of gates that you can choose. You could also extend it, and your result would not significantly differ. So this is an SU11 subalgebra of generators that preserve momentum, and it makes working with these states very easy. All right. Now, in general, all the wave functions around, along the circuits are, like you see that we have 3 gates, but one of them gives an overall phase. And so eventually we have just 2 directions along the circuit. And these 2 directions can be encoded in a single complex function that I call gamma plus. And so it turns out that I can just draw all my states using this gamma plus that has a real component and a complex component. If I require my trajectories to be unitary, meaning that I can extract an additional part that does not act on mu to translate this guy that is actually not a unitary to a unitary, then I will get a constraint on gamma plus, and as a consequence, gamma plus has to lie inside the disk. So the norm has to be smaller than 1. And inside this disk, the reference state is simply gamma plus equals 0. This is very obvious to see. And it's also easy to prove that the vacuum state is the state with gamma plus having a certain value along the real axis of gamma plus. Now, if I write the Fubini's 2D metric for states of this form, then I will find that the geometry of distances of the states that are described by this gamma plus is simply the Poincare unit disk with the usual distance that we are all used to. It's written here in the corner. And then I can use this to evaluate the length of the geodesic that goes from the center to the vacuum state. In this case, it's just a straight line. And what I get is the following expression that depends on the scale of the reference state and is bounded by some cutoff, so it's divergent. But the structure of divergences, so that's interesting, has a volume law and starts to be divergent 1 higher order than entanglement entropy. So entanglement entropy usually starts with cutoff to the power d-2, and area law, complexity starts with a volume law. Okay, and of course then there are additional studies of fermions and thermophile double states, etc. So just remember that the leading divergence of complexity goes like a volume law and depends on the properties of the reference state. And this I will tell you in a bit, that it matches well with holography. All right, so this was complexity of pure states. Let me also tell you something about the complexity of mixed states. So if we want to define complexity of mixed states, we are now dealing with the density matrices that don't factorize in a very obvious way. So they are just sum of different contributions. And in this case, there is a very natural definition that appears in the literature of quantum information, which defines the complexity of mixed states as basically using the purification of the mixed state. So what we do is we imagine we are interested in constructing a mixed density matrix rho A on some amount of degrees of freedom A. We take this state and purify it using additional degrees of freedom AC. And on the combined system of A and A complement, the state is pure. Of course, there are many ways of doing that. So for a given mixed state, there are different ways of purifying them. And so we can ask the question, starting with the reference state, what is the closest purification using our previous definitions of complexity of pure states? So to go from the reference state to the target state, I don't need anything but the definition for pure states. And now I'm going to just look at all possible purifications and which one is the closest. So the purification complexity is going to be defined as the lowest value of the circuit complexity optimized over all the possible purifications of a given mixed state. So let me give you a simple example. So a simple example is the following. So imagine that I'm looking at a Gaussian mixed state of a single harmonic oscillator with frequency omega. The most general density matrix of this 1 degree of freedom can be constructed by multiplying by each other 3 elements. The center element, that is the important one, is the reason for the mixture, is simply the thermal density matrix that we all know and love. And then I can also do something else, is I can squeeze the operator, which just rescales the position in position space representation. So that's the most general mixed state of a single degree of freedom. It has 2 parameters, the temperature beta and the squeezing. Now, the most general purification of this single harmonic oscillator is using 2 harmonic oscillators, and it can be constructed using the very symmetric and famous purification, which is the thermophile double state. So basically this combination of the energy eigenstates of the oscillator. And the squeezing of the first oscillator, in order that when we trace the second one gives the state, has to be the same parameter R, but there is also a squeezing of the second oscillator, which is a free parameter. So when I talk about complexity of purification, I'm just optimizing over all the possible parameters S of the purification to see what is the minimal closest pure state on 2 oscillators. I'm going to tell you what this tells me in a second, but are there any questions about this, the idea of complexity of purification?
If you have any questions, you can ask.
All right, so if not, I will tell you a little bit what this tells me. So in general, if I try to do this optimization, I'm going to get a result that looks quite ugly. So I'm not going to present it in broad generality, but I can focus, for example, on the state that is the thermal state, so the one with R equals 0. So if I focus on the thermal state and I ask what is the optimal purification, for example, I could ask, is it the thermophile double state or is it something else with some non-trivial value of S? So we did that. That's easy to do analytically. And what we found was that the complexity of the thermal state defined through the complexity of purification has 3 different regimes, one above, well, let's say 2 different regimes, where the result for the complexity differs depending on how the scale of the reference state and the frequency depend on each other. when I'm going to move to talk about the full field theory, this is at the moment a single oscillator, but moving to talk about the full field theory is very easy, just replacing omega by a series of frequencies of the different oscillators. This term diverges for very large omega, and so it's going to give rise to UV divergences. Now I told you that I'm interested in asking if the optimal purification of the thermophile double state is if the optimal purification of the thermal state is the thermophile double. The answer is no. So it turns out that if you evaluate the complexity of the thermophile double, you will find this expression, which in some range of, in some specific range of parameters that is actually quite narrow. It is true that the thermophile double is the optimal purification of the thermal state, but in most of the ranges of frequencies, it's not. And in fact, there is a factor of 2 between the way the thermal state diverges and the way the thermophile double state diverges. And I will explain that in a second, like why it's natural. All right. So now if we take these statements about a single oscillator and we go to a free bosonic CFT, all we have to do is simply replace the frequencies by the frequencies of the oscillators in the bosonic field theory and simply integrate over momenta. So if we do that, we will find that, as I said a second ago, that the thermophile double is actually twice as UV divergent as the thermal state. And the reason is because we are working way too hard when we build the thermophile double state. We have two sides and we are making a lot of efforts to mimic correlations on the second side, which is then going to be traced out because we are not at all interested in it when we talk about the thermal state that lives only on one side. So basically, we are working twice too hard. And this is also the case in holography. So in holography, there are conjectures also talking about the complexity of subregions or the complexity of thermal states. And in holography, the thermophile double state is dual to an eternal black hole, while the thermal state lives on one side. And if you evaluate certain quantities that are divergence due to the proximity to the boundary, the thermophile double state is going to have two boundaries, while thermal state only has one, so will be twice less divergent. So this also matches very well with what one finds in holography. All right, so that was for thermal states. Another famous mixed state is the vacuum, is the subregion of the vacuum, actually. So another mixed state that we can look at is to look at the subregion of a free bosonic vacuum in 1+1 dimension on the periodic lattice. This we cannot do analytically, but we can definitely do it numerically. So we can just trace out a certain portion of the space and look at the density matrix that is obtained in this way. And optimize numerically over the, just put it on the lattice, and then every lattice site has certain amount of parameters associated to it in the wave function. So just optimize numerically over these parameters. So we did that for lattices of a size of 1,000 sites. And we plotted the complexity as a function of two things. One is the size of the subregion, and the other is the cutoff. And from these two plots, we could reconstruct an expression, closed form expression for the complexity. And what we found was the following. So we basically found that the complexity had again, a volume law, so was proportional to the size of the subregion, with a prefactor that depended on the properties of the scale of the reference state. And there was a subleading divergence, which was logarithmic, which was not present when we talked about the complexity of the full state, and a constant. So as I said, there is a volume law. And one thing that was very, very interesting that we discovered in this work was that if we focus on the subleading logarithmic divergence and we make some more efforts to fit it together with the finite term, we find the following expression. So we basically find an expression that is proportional to the entanglement entropy. So it's not quite log L over delta, but from the finite part, you can extract a sine of pi. L is the size of the subregion, and big L is the size of the full circle. So this is a very funny looking expression, but it's very famous if we studied entanglement entropy on a finite interval. And so it turns out that this first subleading correction to the complexity has a very, very close tie to the entanglement entropy. And this appears in other contexts as well.
Sorry, so I'm just trying to wrap my head around the significance for the last comment that you made.
Yes.
Can we then say that complexity is going to increase if the amount of entanglement increases? I mean, so what is the significance for this last comment that there is a piece that you can identify as entanglement entropy?
Right, so you could construct from the complexity certain quantities, like the mutual complexity. So, I mean, you would have to cancel, of course, the most dominant term on the lattice is the leading term. But if you would look at the complexity
but I'm just wondering,
region,
the first term, this leading dominant term, that does it have anything to do with the amount of entanglement that is present? Is there some sense that you can think of that as sort of independent of the amount of entanglement?
I think you can, well, I don't know if you can think about it as independent from the amount of entanglement, but you can definitely construct quantities that cancel it. And these quantities will have a leading term which just goes together with the entanglement entropy. So for example, if you look at the complexity of the full region minus this guy minus the complement, then you would be canceling the volume law. And so you will be left with a quantity, which you can call mutual complexity, which, yes, increases and decreases with the entanglement, exactly.
Mm-hmm. Okay, thank you. Another thing, Shira, I just wanted to clarify a small thing, that in the description that you presented so far is quite general. I mean, you have not assumed nice properties that quantum field theories satisfy, like in unitarity, or have you assumed unitarity implicitly somewhere?
Yes, I think we definitely assume things about the range of parameters that are related to unitarity. I mean, in the first construction that I showed you, this was like the gamma plus lied within the circle. To say that practically changes the result, yeah, I mean, do you have something specific in mind? Like, do you want to look at non-unitary examples?
I'm just wondering if this statement that complexity increases with the amount of entanglement is only a statement that you can make in unitary theories, or is this a more general statement that you can make?
No, it sounds reasonable. That I mean, everything that we've been doing is, I mean, you know, free field theories, and I mean, I think we are focusing on unitary examples. Mm-hmm. No, but I mean, maybe that's the reason, or maybe the reason is somehow tied to this, but I don't have too deep observation about it.
Okay, thank you.
Sorry, just going along this last question, can I not, in a quantum mechanical system, can I not look at a quantum open system and try to address the kind of question, because there I know the evaluation will not be unitary, and can I not ask the question that Anindya was asking?
So you mean by focusing on the subregion somehow? I see. No, yeah, that might be true, but of course you understand that all the systems are like taken as portions of systems, that the whole system is unitary. So I'm not sure. Yeah, I don't have anything too smart to say, but maybe we can discuss a bit more. Like, you can tell me what you have in mind in the maybe after or in the discussion session, and I can understand a bit better what you have in mind.
Sure. Okay. Just to understand, one point is that here all the field theory that you have taken, they are well defined, meaning they are unitary. Those are the examples that you have taken, and then you are trying to understand things.
Yes, absolutely. So it's like this kind of. You know, at some point there were these calculations of transport coefficients in hydrodynamics, in the free field theory and in the holography, and when they gave the same, you would say that, I suspect that it's the same everywhere. It's this kind of argument, because we don't know a lot. I mean, we know very little how to go beyond free field theory. I mean, now we know a bit more, but but all these arguments are based on similarities between free field theories and holographic systems, which are clearly not the same. But when you talk about properties like the structure of divergences, these are things that morally behave similar in holography and in free field theory, and you see that also when you talk about entanglement.
I mean, I have just one quick comment. I mean, what if I understood that? So if you consider those other complicated systems like this, saying open system, I think probably this Gaussian purification will not be enough. So that may be the point of concern. Means here you have done a Gaussian purification. Means you purified it to a Gaussian state, but that might not be enough for other cases.
Yeah, that's definitely possible.
Hey, Shira, can I ask you a short question? So if you look at the structure of the complexity, the C1, which we have calculated, so the first term seems to be depend on the reference state.
Right.
So if I look at the mutual complexity, it seems to be independent of the reference state. So is it
No. That's misleading. That's there should be a proportionality sign. There is also a prefactor that depends on the reference state.
Okay. So it is not universal as one. It's not, right? It also depends on.
No, definitely. But the point is that, you know, this prefactor that is, say, a function of the reference frequency, then multiplies a construct that, you know, is quite complex, depends on the size of the subregion, depends on delta, etc., in some particular way that is maybe typical of the fact that, I mean, this is almost massless case, so it could be typical of, you know, certain conformal transformations that you can do on the circle, but basically it just behaves in this typical way that you can fit, and you will find, I mean, it's not an accident, let's say.
Okay.
So it could be that the same, you know, symmetries that tell you that the entanglement needs to depend on this length scale in this way also influence the subleading term of complexity.
Okay. Thanks.
All right, so a little bit about holography now. I think this is part 3, right? Yes. Okay, so all I've told you so far was for free field theories, and now I'm going to talk a little bit about holography. In holography, I told you that one of the signatures of the relation between complexity and black hole interior had to do with the time dependence. So now I'm going back to the spin chains, and I'm just going to tell you a few expectations that we have about how complexity evolves with time. So in general, the holographic systems are what's known as fast scramblers. So these are systems that spread the effects of localized perturbations over all the degrees of freedom in a time which is logarithmic in the entropy, so very fast. And in systems like that, the expectation is that the Hamiltonian evolution is the shortest way. So basically, okay, sorry, let me just roll back a little bit. In these systems, we focus on a specific unitary, which is the time evolution. That's the way that we tie the complexity property to the system. We ask how complex is the evolution in time of a given system. So the question is, what is the most efficient way to build e to the minus IHT? Now, since these systems are chaotic and complicated, for generic values of their couplings, etc., the expectation is that there are no, say, magic shortcuts to construct the time evolution, but rather the most efficient way to build the time evolution is simply by discretized steps of the Hamiltonian that don't cancel between them. And so from this, and also the properties of SU2 to the n that I told you before, for example, that the furthest unitary was at a distance exponential in the number of spins, it's very easy to make certain counting arguments to predict that the complexity is going to be increasing linearly for a time which is exponential in the number of spins. And then when it reaches the edge of the group, it's going to start fluctuating. So remember this about how complexity is expected to evolve in time in chaotic systems. I'm making this argument on spin chains because we don't yet have the abilities to study it properly in field theory for such complicated systems. And now I will tell you what we say in holography. So in holography, there are two proposals for what is conjectured to be the dual of complexity. The first one is the complexity equals volume proposal, which says that the complexity is equal to the volume of a maximal space-like slice that anchors at the boundary at the time slice where the state is defined. And so the complexity is simply a maximal volume. And alternative proposal talks about equating the complexity to the gravitational action of a region in the bulk, which is some kind of this null diamond, which is bounded by light sheets. It's known as the wheel or the wheat patch, and it's basically the union of all the space-like slices that anchor at the time slice where the state is defined. The action proposal was said to have a number of advantages on the volume proposal, since it doesn't involve an extra scale, like the units work out better, and it doesn't single out a special space-like slice. But I will tell you about both of them. So divergences first. These volumes and action are divergent. And the reason is, well, we said in field theory due to short distance correlation, but in holography, this is due to the fact that the volume and the action go arbitrarily near the boundary where the metric diverges. And so in order to get a finite quantity, we as usual need to regulate, for example, by placing a regulator surface at z equals to delta in a Pfefferman-Graham expansion. And when doing that, we will obtain a series of divergences, starting with a volume law diverging with the delta to the d minus 1. So n proportional to the central charge. So all of these properties are similar to what is found in field theory. And when talking about the action, there is one subtlety that has to do with the null boundaries. There is certain ambiguity in the gravitational action on regions with null boundaries, and one has to add a counter term there. And this counter term depends on an arbitrary scale, which we call LCT. And that scale appears in the result for the action complexity in a place very, very similar to what appeared the scale of the reference state when we talked about the free field theories. So the another elaboration of the conjecture says that these free choices of counterterms on the null boundary actually reflect the choice of the unentangled reference state in the field theory. So this I said, volume law, counterterm on the null boundaries, and the result is proportional to the central charge. All right, so these were the divergences. Now let's use the conjectures to talk about the growth of the volume. So I told you that all the story started from the puzzle of why the interior of black holes go forever, and now I'm in the position to tell you exactly what I mean. So if we focus on a setup that we know very well in holography, on the eternal ADS black hole, which is dual to the thermophile double state, then time will be running. The thermophile double state lives on two copies of a field theory. One lives on the right boundary, the other on the left boundary. And as time moves forward, this thermophile double state gets modified. It gets more and more complicated. And what I have to do according to the proposals is to look for the volume that connects the thermophile double anchored at the relevant time slices of the boundary. And since every point in the diagram is the sphere at time 0 on both sides, the maximal surface is simply a straight line going through the bifurcation, or basically this kind of tube, the wormhole. As time progresses, the wormhole gets longer and longer and longer. And this persists for a very long time, as long as the semi-classical gravity approximation is valid. And the claim is that this is exactly what we expect from complexity. And that's what Saskin said. He basically said entanglement is not enough, since entanglement does not keep growing for a very long time. It saturates after a time which is proportional to the size of the subregion that we are studying the entanglement for, while complexity keeps growing for a long time. So why do we think that that's complexity? So first reason is that we know of a very good analogy between the space of ADS and tensor networks. In particular, we know that the pattern of entanglement in a state can be defined and visualized using the geometry of an emergent holographic dimension. And in this picture, it's very natural, since the tensor network lives on a slice of ADS, to simply say that the number of gates is the geometric volume. The second reason I already told you was the late time growth, was that we expect complexity to grow linearly for a very long time, and also the volume and the action grow linearly for a very long time at a rate which is proportional to the energy of the system on the boundary or the mass of the black hole in the bulk. And the third evidence, which I think is the most convincing one, is what is known as the switchback effect. So that's the study of the effects of perturbations on complexity. And the point is that if we perturb the system, we can look at an operator which is going to encode the effect of this perturbation, and is basically constructed by running backwards in time at time t, adding a perturbation, and running forward in time at time t. So this tells you what happened, the complexity of this operator. It's known as the precursor. Now, if there is no perturbation, the backward and forward evolution cancel. The backward and forward evolution cancel, and so the complexity of the precursor is simply zero. You don't need to build anything. This is simply the unit operator. But if I do add the perturbation and the system is chaotic, then let me tell you what I expect from spin chain arguments. So imagine that the unitary evolution in time is most efficiently constructed by a product of gates, G1, G2, so on, until Gn. This is the perturbation, and that's the backwards evolution. And so if I ask what is the complexity of this operator, asking how the addition of the perturbation influenced the system, at early time, I would have one gate here and one gate here, then two gates here and two gates here, and that's going to depend on the time where I inserted the perturbation. Now at zero time, I just have the perturbation itself, so the complexity is one. There is just one gate, simple gate, that generates the perturbation. As the time of the insertion of the perturbation goes back, the complexity is going to increase. So here I would need 3 gates to construct the state. But that's not always going to be the case. So that depends on if the perturbation commutes with the gates of the unitary or it doesn't. For example, if the perturbation commutes, then we could cancel those gates and we can still construct the precursor at time t by just 3 gates. And basically what you see is that there is some kind of epidemic model of the qubits that gets infected. And so the complexity increases relatively slowly at early times until a certain time, that is the scrambling time, where the perturbation has infected all the qubits of the system. And at this time, nothing cancels anymore. So as time evolves, the complexity is growing simply linearly, one gate from the left and one gate from the right for every time step. So this can be very easily modeled by a completely standard epidemic model. And this standard epidemic model predicts, now clearly we all know, exponential growth at early times and linear growth after the scrambling time. If I denote by L the characteristic time scale, the scrambling time is logarithmic in the number of spins or the number of degrees of freedom in the spin chain. And the complexity is expected to almost not grow, but actually it's growing exponentially at early time and then follow a linear growth at times after the scrambling time. Now, this can be reproduced in holographic systems very easily by simply inserting a shockwave into a black hole. The shockwave mimics the perturbation to the field theory from one of the sides of the thermofield double. And so the perturbed thermofield double is simply applying a precursor operator running backwards in time, putting the perturbation and running forward in time. And if we focus on the complexity at t equals 0, we will simply see something that is the complexity of the precursor. So we did that.
Just sorry to cut off. Just given the interest of time, I think it's like maybe 5 minutes.
All right, sounds good. I think I actually, it looks like there are still many slides, but that's not true.
Oh,
they're just like, I think just two. Sorry about that.
No, sure.
All right, so we did that numerically in holography by studying these geometries, the maximal volumes, etc. And that's what we found. So we found these plots that are the complexity as a function of the time of the insertion of the perturbation. First for light shocks. So this is when focusing on shocks that just increase the mass of the black hole or its temperature by a very little bit. You can see that there is a plateau where the complexity is simply not changing at all. And then at some time, which is the scrambling time, there starts to be a linear increase. You can fit the time in which this transition happens, and you will find exactly the holographic famous scrambling time, which can also be found in other ways. And then you will find a linear increase delayed by the scrambling time, which is exactly what you would expect if you were thinking about complexity of chaotic spin chains. At early times, just to isolate the effect of what's happening at early times, we differentiated those plots such that this becomes a constant, but this is still exponential, and then take the logarithm, so you will see a linear increase at early times. And so basically at early times, the complexity increases exponentially, suppressed with the scrambling time and with the characteristic exponent, which is the Lyapunov exponent for maximally chaotic systems. We also repeated these same arguments for heavy shocks. So for a large perturbation, where it is expected from spin chain arguments that at early times, the rate of change of complexity is going to be proportional to the difference of masses, and at late times to the sum of masses. And since we are throwing a very large perturbation on the system, it scrambles almost right away. So the scrambling time is expected to be much shorter. And indeed, if you do all these numerical studies of volumes in the presence of black holes, they behave exactly in this way. So they start with the difference of the mass, and they get to the sum of the mass after a certain scrambling time. So this matches exactly the expectation from the circuit picture. And you can see, well, you saw previously that you could diagnose scrambling and you could diagnose chaos by just studying shock waves and their influence on the complexity. Okay, so that's basically all I wanted to tell you. Let me just summarize. So I showed you that the complexity is a very interesting and new tool from quantum information that can teach us about the interior of black holes. We defined it in QFT in 3 setups. We explored the time dependence and how it's affected by perturbation. And I showed you how scrambling and chaos can be analyzed using the complexity. And so what's next? So the first thing that is obviously missing is complexity in strongly interacting systems. So all I told you was about free systems. There are also works about weakly interacting systems by some people in the audience, and some very recent new developments in CFT using the generators of the conformal groups as gates. And I hope that next time that I talk here, I will be able to report also some progress on this. Another interesting thing, actually, these are 2 points, is to study the whether the geometric tools that we have developed for complexity can be used in real-world quantum simulation or quantum applications for quantum computing, and also whether the idea of complexity related to Hamiltonians, etc., can help us relate complexity, study properties of physical systems, for example, phase transitions, etc., through the complexity. And then there are more holographic questions. Where exactly is the information about the interior stored? Can we use complexity to understand better the bulk boundary map? And that's it. So basically, there's lots to do. And thank you.
So thank you, Shira, for the wonderful talk. And I think we can open up a little bit to take some questions, but I request to keep the questions brief, actually, given the interest of time. So you can ask the questions to her.
There is a question in the chat box, actually.
Chat box?
Yeah, so it says, Sachin Chauhan, can we treat complexity as a more general measure of entanglement?
Yeah, I think that's a good way to think about it. I mean, I think it's exactly. I mean, the idea is that the complexity, especially when you talk, for example, about thermophile double states, is very sensitive to the phases that are accumulated in the system during a long evolution. So it remembers. That's the advantage it has on the entanglement, that it remembers developments of the system for a longer time. But definitely what it's studying is correlations. And I think you saw when I was talking about free field theory that, okay, so we can read the central charge and we can read the entanglement, but we don't study necessarily a lot new about the properties of the system when we are in static situation. The place where complexity becomes really interesting is when you talk about dynamical situations, because it has a long-term memory. In a sense, but yes, it's definitely measuring correlations or quantum correlations in the system. We can call it entanglement, broadly defined.
But there could be, you could be still be counting non-entangling gates, and there could be many of them. And so you could have a large amount of complexity without having entangling gates, right? So in that sense, wouldn't the two things be distinct? That the number of entangling gates could be substantially different from the number of, say, the kind of Hadamard gates or single qubit gates.
You can't. I think the point is that if you think about the spin chain, then now I can tell that you're not hearing me well. Can you hear me well?
Yes.
Sorry, I get a small notification. So it's not true that you can get to very complicated states using only non-entangling gates, at least scaling wise, because just think about the spin chain and how many non-entangled states you have, right? I mean, you have up, or up, down, up, etc. But you have a maybe exponential amount of possibilities, while you would have a doubly exponential amount of possibilities for the complexity, right? Because it's just looking, when I wrote it with alpha, beta, etc., it would be one of those alpha set to 1 and all the others set to 0. It's much less than all the possibilities of a complex phase in front of all the spin combinations. So it's really just a much narrower set of states that you can reach this way.
That's true. Yeah. Thank you.
Yeah.
I think Ornov has one question, so I request him to ask directly.
Okay, so you can hear me, right?
Yes.
Okay, perfect. So it's a very brief question. It's probably related to some of the questions that were already asked. So I'm just curious how much in general is known about, let's say, constraints coming from unitarity to complexity or its time evolution and so on and so forth. So if you can comment on that, that would be great.
Yeah, I mean, I don't know how to give you I mean, I don't have a very insightful answer. I mean, I have, I can point you to the particular example of what tells me in the free case. But I'll tell you what, let me think about it, because I think you want something more than that. And I will be here in the discussion session, and maybe I will have something wiser to say about it.
Okay, that's fine. Thank you.
Any other questions?
Arpan, this is Shurita. Can I ask a short question?
Ask.
Okay. So this entanglement entropy has this special properties like strong subadditivity identities. And then you also see that the holographic prescriptions also almost automatically obeys those identities. Is there any such test possible for this volume proposal? Or actually?
Yeah, so I think, I mean, I don't think these have been worked out, but I think that you start from a distance function that has certain properties, and you probably can prove additivity properties, but I don't know that this has been done.
Thanks.
perhaps we can, there is one more question in chat. Perhaps this is the last question. So I'm reading it. So the question is that, is there any reason to think that complexity should have a higher bound or saturation value for a particular system?
Yes, so well, so let's say this complexity is a property associated with a state, right? So a state can in principle be defined without reference to any system, but if you want to refer to a system, then I would have to understand the question as asking about the complexity of, for example, the time evolution of the Hamiltonian of the system. So you would ask, is there what constrains the how much increase is happening in the complexity of the unitary of the time evolution? And in this case, I think for very simple system, it does not go that high. So it increases for a very short time, which is proportional to the inverse temperature, for example. That would be the case for 3 systems. So the time evolution in 3 systems is very, very simple. While the one of chaotic systems, from these generic counting arguments of how the volume of the unitaries needs to look, should be much more complicated and increase for a long time. I think the question of, for specific values of the coupling, how long the complexity increases is very hard. And so the way these questions are usually answered is in an averaging style. So saying the volume is such that for most of the couplings, you need to see a long time increase because you need to fill the group by a certain counting argument. But I think if you want to answer the question for a specific, very complicated system, for a given Hamiltonian, then this is a very hard question. It's the same that happens when you average on couplings in SYK. Like certain questions become much easier to answer in an averaged way. So all these arguments, you should think about them as an average statement for almost all the values of couplings J in the Hamiltonian of n spins made from products of Pauli matrices, you will have a long time increase. That's the way to think about them.
Okay, so we thank Shira again for the wonderful talk, and she will be around at the discussion session, so we can ask her more questions. So thanks, Shira, and we end this.